Now the next one is a maximum of 298 milligrams given lead nitrate, and it is dissolved in how much 750 milliliters, and calculate the sodium bromide solution molarity, right? The molarity. So the first thing, this kind of, when you have two solutions given, do the double replacement. You just plug in lead nitrate and sodium bromide and see what can happen, right? So use the solubility chart, and it'll give you here PbBr2 and NaNO3. For me, I remember nitrates and sodiums are all it's a balance equation first. So once you have the balance equation, see aqueous, solid, and aqueous, that is from the solubility chart. You don't need to memorize it, right? Now, so all the aqueous normally in the left side is mostly aqueous. So if you don't know, you can't figure out. So bank on its aqueous. That very rarely you're going to get a solid in the left side. Okay. So that's really when your teacher or prof want to really trick you. But normally it should not be the case. Now, so you have the formula equation on the top, and then you're going to do the total ions, simply break into ions, right? Two nitrates, one lead, two sodium, two Br, and so on. And that make sure liquids and solids are not broken into ions. That means PbBr2 gonna stay as a solid, right? Net ionic, just cancel numerically. Two nitrate cancel to two nitrate. Two sodium cancel to two sodium. So that's numerically you have to cancel left to the right, right? What is left over? Pb2 plus 2Br minus come together to make PbBr2 solid, right? That's our KSP. Now that's how we figure out from the double replacement from the two solutions to the KSP. Okay. Now there is another way, a shortcut, but I will try to show you in a different one. This is much complex to show that. So PbBr2, you write the normal KSP equation, right? And then you can also do the solubility. You lose minus S and you make the solubility 1 and 2S because of the 2Br, right? That's the coefficient. So if you have those, now you can calculate the KSP, you can predict on solubility, anything you want, right? So these are the two steps. Double replacement, figure out which one will give you the KSP, write the KSP. Usually it's better to write this KSP law, which is the expression have the two ions, ion product, right? And the S and the 2S goes inside, so replace the Br and the Pb2 plus, and no make mistake, 2s to the 2 here, power of, right? And now we can calculate the KSP, or you can go back and forth, right? You can, if you're given the solubility, you can calculate the KSP. If you're given the KSP, you can calculate the solubility, right? So check my previous ones, you can figure out. In this case, we're going to use the book value 6.6 times 10 to the minus 10, the KSP, because we are looking for the bromide molarity, right? In this case. So um, PB2 plus, we have to figure out, because we are given some milligrams and some milliliters, right? We're going to figure out that. So how do we do that? So it's a separate math. I would say do it separately. Don't plug into the same KSP formula, right? Let's do it separately. So 298 mgs dissolved in the 750 milliliter. I will plug in as liters, 0.75 liters. So that's the best way to write that data. Now you have mgs over liter, but we need the moles over liter, right? So what we can do, just plug in the grams. So divide by 1000 the 298, you get the 0.298 grams. Now we have grams over liter, easily use the molar mass. To cancel the gram to gram, you get the mole over liter. That's what the molarity, that's what we need, right? So these kind of little conversions, not part of the big question, so do it separately, right? So in this case, the molar mass is 331.2. That's basically for the silver nitrate, and that's the lead nitrate. So lead nitrate, And now you can do the math here and get the molarity for the lead nitrate, because that will give you directly the molarity of lead, right? So let's get the lead nitrate value here. 0.298 divided by 0.75 divided by 331.2. So that'll give you molarity of 0.0012. That's the one Pb2 plus the same, because it's same coefficient. Now you can plug in the Pb2 plus value, and only thing we're looking for Br minus. Unfortunately, it's to the power of 2. Don't drop that one, right? So now you divide 0.0012 and take the BR out. So that's the KSP divided by 0.0012, and the BR2, in order to get rid of the power of 2, you're going to have to take the root. So let's take the root of each side. So that will cancel the root and the BR squared. So therefore, now you have bromine concentration. Bromide. If you have the bromide concentration, it's the same as sodium bromide concentration. So that's it. So this math, just do the math, and then the big concept is we plug into the KSP expression, and that's how you do it. So your value ends up with 7.4 10 to the minus, actually 9 minus 4, right? And then that's the answer for that one. Okay, so we have another question. Let's see. Yes, we can also write, actually, bromide molarity is same as one bromine is one sodium bromide. So the Br to Br cancels out. You get the sodium bromide. So that's a little bit more explanation on how do we get to the sodium bromide molarity used in this question. Okay, all right. Thank you.